The Brachistochrone Curve. The question we will be answering in this video is, which is the fastest path to go from point A to point B, being gravity the only force acting on the system? Of course, point A and point B have different heights, and they are not one under the other. To solve this problem, two different factors must be taken into account: the acceleration gotten from the slope of the path and the distance traveled. Therefore, we will have to find the right balance between both of them. This problem has been around from a really long time. In fact, different scientists have tried to solve it. For example, Galileo thought that the right curve was a piece of a circumference. Nevertheless, Johann Bernoulli came up with the correct answer in the 18th century, analyzing the behavior of the light and based it on Snell's law. He realized that this path was a cycloid, a curve created by a point on the perimeter of a circle when it rolls in a straight line. We will now demonstrate this path, called Brachistochrone, is in fact the fastest one from point A to point B, with the conditions explained before. For that, we will compare it with other possible curves, a straight line and a steep path.
So we first started by drawing a circumference so we could later draw the cycloid. We cut it out, polished it, and later we made a hole in it, and once it was ready we rolled it on a plane. So we could get the perfect curve we're searching for, and there it is, our Brachistochrone. Then we kept on building the platform that was gonna hold the curves. We tried to get the best cycloid we could, and we located in between the other two paths. After that, we just had to put into practice what Bernoulli said and prove that the Brachistochrone is actually the fastest way to get to point B. As expected, the ball on the steepest path got the greatest acceleration and was the first one at the beginning. However, the ball on the Brachistochrone catched it up and got first to the end. On the other hand, we have the straight line, and we can easily say that even if it's the shortest path, it's not the fastest one. Apart from this, we also made a second platform with the cardboards previously cut out. As expected, the outcome didn't change, and the rolling object of the Brachistochrone took the smallest amount of time to arrive to the end of the trajectory. Nevertheless, this is not where the Brachistochrone stops surprising us. In fact, this curve is also known as the Brachistochrone Curve, and as the name implies, no matter where the trajectory is begun, the ball will need the exact same period of time to arrive to the end. To prove this, we've made two identical cycloids and then we let the balls fall from different heights.